Hello everyone, welcome back. This is the fourth video for the Solving and Graphing Polynomial Equations worksheets. I would love for you to join me in working through these notes and examples so that you can just be extra brilliant the next time I see you. So go ahead and get ready with some highlighters and pencils and let's get started. So going back to a previous problem seen in the previous worksheets and notes, let's solve and sketch a graph of f of x, which is 8x to the fourth minus 2x cubed plus 31x squared minus 8x minus 4. So from worksheet number 2, we know that the possible rational roots are plus or minus 1, 1/2, 1/4, 1/8, 2, and 4. And from worksheet number 3, we determined that Descartes' rule of signs chart was for the positives 3 and 1, negatives 1, and complex or imaginary either 0 or 2. So in addition to using Descartes' rule of signs chart and possible rational roots, the upper and lower bounds theorem can also be useful when trying to find these solutions. Okay, so we have the upper and lower bounds theorem. Suppose c is a positive number and p of x is divided by x minus c using synthetic division. If the coefficients in the resulting quotient and remainder have no changes in sign, in other words, they're all positive or all negative numbers, then p of x has no real zeros, and that's just real zeros or x-intercepts, greater than c. Thus, c would be the upper bound for the real zeros of p of x. On the other hand, we can also look at if c is a negative number and p of x is divided by x minus c using synthetic division. If the coefficients in the resulting quotient remainder alternate in sign, so plus minus plus or minus plus minus plus, then p of x has no real zeros less than c. So before we had greater than c, now we have less than c, because this time we're talking about a lower bound for the real zeros of p of x. Since we know that we have a positive and negative real root, let's look what happens when we try 1 and negative 1 in synthetic division. So when we have 1, and here are all of the coefficients in our constant term from our polynomial, we end up with all positive coefficients here. And whenever we look at negative 1, notice it's positive, then negative, positive, negative, positive. So they alternate signs. So they are not the real roots because we had a remainder other than 0, but we still got some information from them, and that 1 is going to be the upper bound and negative 1 is the lower bound, which means that our positive real root is less than 1 and our negative real root is greater than 1. Therefore, we should try positive roots less than 1 and negative roots greater than negative 1. So in other words, we're trying out the roots that are between negative 1 and 1. So we had plus and minus 1/2, we had plus and minus 1/4, and we had plus or minus 1/8. So really you just pick one of these and start using synthetic division and see if you can get a remainder of 0, which means that it would be a root for that polynomial. So if I start out with positive 1/2, and again I've got the same coefficients and constants, so I have 8, negative 2, 31, negative 8, and negative 4. So we'll do synthetic division on that one. We bring down the 8 times 1/2 is 4, plus negative 2 is 2. 2 times 1/2 is 1, plus 31 is 32. 32 plus 1/2 is 16, plus negative 8 is 8. And 8 times 1/2 is 4, plus negative 4 is 0. That's a good thing. That means that 1/2 is one of our roots. Okay, let's try negative 1/2. see if that one works. So again, we'll go back to using the numbers from the original polynomial. So if we bring down the 8 times a negative half is negative 4. So we add and we get negative 6 times negative a half is 3, plus 31 is 34, times negative a half is negative 17, plus negative 8 is negative 25, and then that times negative a half is positive 25 over 2, and when you add that you get a number that definitely does not equal 0, which is 17 halves. So this one is not one of our roots. Let's try negative 1/4. So we have 8, negative 2, 31, negative 8, negative 4 again. Let's bring down the 8. 8 times 1/4 is negative 2. Plus negative 2 is negative 4. Times the negative of 4th is 1. Plus 31 is 32. Times negative 1/4 is negative 8. Plus negative 8 is negative 16. And that times negative 1/4 is 4. Plus negative 4, which is 0. And that's good again because now we know we've got the negative 1/4 is a root as well. Okay, so far we know that we have solutions of 1/2, and we also have negative 1/4. But according to our chart, we either had 3 positives and 1 negative, or we had 1 positive, 1 negative, and 2 complex. Well, we do know that 2 of our roots so far, we've got a positive and a negative. But let's see, we have factored out, we divided different ways of thinking about this. We've either divided out this factor or we've used synthetic substitution to see if it was 0 to determine if this was a root of our polynomial. Either of those things you can get from this synthetic chart here. So I'm going to say that, okay, we took out the x minus 1/2. And when we divided out the x minus 1/2, or when we factored out x minus 1/2, we were left with 8x cubed plus 2x squared plus 32x plus 8. So let's just see if we can factor this. I do see a greatest common factor of 2, so I'll just put that in the front. And we have x minus 1/2. And so now what we've got is 4x cubed plus x squared plus 16x plus 4. Now I have 4 terms. Let's see if factoring by grouping works. So 2 times x minus 1/2. And then my greatest common factor on my first group is x squared. And then I'm left with 4x plus 1. Greatest common factor here is 4. And again, I'm left with 4x plus 1. So it looks like the factoring by grouping works. So then I have 2 times x minus 1/2 times 4x plus 1 times the x squared plus 4. Okay, so looking at each of these factors here, if I set them equal to 0, I'll get x is equal to 1/2. Here, I'll get 4x equals negative 1, so x will equal negative 1/4. And those are the 2 roots we already found. We had 1/2 and we had negative 1/4. But then for this x squared plus 4, when I solve for x, I'll subtract the 4, so I'll get negative 4. So when I take the square root of both sides, I get x equals plus or minus. The square root of 4 is 2, but then that negative means we've got 2i. So as it turns out, we have 2 complex imaginary solutions, which will complete our 4 solutions required for this quartic polynomial. So we have solutions of 1/2, negative 1/4, and positive and negative 2i. Okay, so now that we know all of our roots and we're wanting to sketch a graph of this polynomial, let's remember a couple of things first. If r is a real number root of the polynomial equation p of x equal to 0, then that means a few things. That if we take that root and we plug it into our function, it will give us a value of 0. That if we know that r is a root of the polynomial, then that means it's also an x-intercept on the graph of p of x. If we know that r is a root of the polynomial, then x minus r is a factor of p of x, and also r is a 0 or a solution of p of x. So this is just reminding you all the different things that r being a real number root of the polynomial means. So roots that are not real are called complex or imaginary roots, and complex imaginary roots always occur in conjugate pairs, as we have discussed in the previous videos. So when graphing polynomial functions with complex imaginary roots, the complex imaginary roots will not show up in the graph of the function as x-intercepts, because we are graphing the function on an xy real number coordinate plane. So since our graph can only have real numbers on it, imaginary numbers will not show up on our graph. So for the x-intercepts, that only includes real numbers. That means our x-intercepts are going to be the 1/2 and the -1/4 solutions that we found, but not the plus and minus 2i. They are solutions, but they are not x-intercepts. The y-intercept is our constant term, which will be at -4. The end behavior, we can already determine this, that as f of x approaches as x approaches -infinity. So as x is getting really, really small, then we'll also determine what it's approaching as x is approaching positive infinity. So whenever x is approaching positive infinity, that's asking what the right side is doing. Well, we have a positive leading coefficient, so that means the right side is going to be going up. So f of x will be approaching positive infinity. On the left side, where x is approaching -infinity, we have an even degree, so the left side will do the same thing as the right side, and it will also approach positive infinity. So we can graph this by plotting our 1/2 and -1/4 as close as you can, and our y-intercept of 0, 1, 2, 3, -4. We know the right side and the left side are going up, so it's like a really tall and squished parabola. That's what it's going to look like. So it looks like there are only 2 solutions, but that's because there are only 2 real solutions, and there are 2 imaginary. Let's talk about one more example before I will let you go. Okay, so we're going to solve and sketch a graph of f of x and figure out if it factors. So possible rational roots, remember we look at the p and the q values. So our p values are the possible factors of, or all of the factors of our constant term, which is only plus or minus 1. And q comes from the factors of our leading coefficient, which is 1, so that's also plus or minus 1. So the only p over q values that we get are plus or minus 1. Okay, now let's look at the signs of the polynomial so that we can fill in Descartes' chart. So to figure out how many positive, we look at the sign changes of the original. So this was positive, this was positive, this positive, positive, and positive. There are no sign changes, so that means we have 0 positive real roots. Okay, and then we look at whenever we plug in a negative x. So negative x to the 4th is still positive, and negative x cubed becomes negative. This will become positive. 4 times the negative x is negative, and then we have positive. So there are 1, 2, 3, 4 sign changes. So that means we either have 4, 2, or no negative real roots. So I'm going to fill in this chart here. So I know I'll always have 0 positive, but I will have either 4, 2, or 0 negative roots. But each row must add up to 4 because that's my degree. So this first one already is 4, so I have no complex for that one. If I have 2 negative, then I'll have 2 complex. And if I've got no positive or negative real roots, then that means all of them, or all 4, would be complex or imaginary roots. Okay, since we only have possible negative real solutions, let's try -1, because remember our possible rational roots were positive and -1. So if we don't have any positive ones, then we can only have a -1. So let's try -1 and see what happens. And whenever you use synthetic division, notice that we get that remainder of 0. And that gives us f of x equals x plus 1 times 1x cubed plus 3x squared plus 3x plus 1. Well, this does not factor by grouping. So there's the possibility that it could be a multiple root. And the reason we're not going to check positive 1, again, we don't have any positive real roots. So we need to check to see if it has a multiplicity, since we can either have only 4, 2, or no negative roots. Well, we found out we have 1, so there must be another one, or 2, or 3. So we will now take, if we've already factored out the -1 once, take this row right here and use that row of numbers because we've already taken out the -1. So if we take out -1 again, notice that, look at that, we are left with another remainder of 0. So that means we have x plus 1 is now a factor twice, and we're left with the 1x squared plus 2x plus 1. Well, the x squared plus 2x plus 1 factors into x plus 1 and x plus 1. So as it turns out, the -1 is a multiple root with a multiplicity of 4. That is an even multiplicity, so the graph will only touch that solution, but it will bounce back off of it since the multiplicity is even. So let's go ahead and wrap this up by graphing. So remember our solutions, we've got x equals -1. It just has a multiplicity of 4. X-intercepts, it means only our real solutions. Well, we've got -1, 0. Our y-intercept is our constant term, which ended with, I know you can't see it on the screen anymore, but it ended with a 1, so our y-intercept is at 1. So if I graph the x-intercept of -1, 0, and my y-intercept of 0, 1, my end behavior, we could also go ahead and fill that out. So as x approaches positive infinity, my leading coefficient was positive, so my right side is going up, so y values are approaching positive infinity. And f of x is approaching as x approaches negative infinity. So as x is getting really small, what is the left side doing? What are the y values going to do? Well, my degree was 4, we had x to the 4th, so that means the left side will do the same thing as the right side. So here it will also approach positive infinity. So there's my right side, and here's my left side. Notice that it does not cross the x-axis, it just bounces right back off of it, and there's our graph. Okay, that's it. We will practice some more of these in class whenever I see you next, and I hope you're having a great day. See you later. Bye.